Then welcome back. I hope you prepared coffee. And we have the second speaker of the day with Simone Henry. And the talk is going to be prodiscrete locales, extensivity, and pro-completion. Simone, take the stage.
Thank you very much. And thank you everybody for coming. So yeah, as the title say, I want to talk a little bit about pro-completion and how to think about prodiscrete locale as a kind of pro-completion. But maybe it's best if I introduce a few things before I explain exactly what I want to talk about. So for me, the pro-completion of a category, I will always take a category C, which has a finite limit. And I'm building it's a well-known construction. We're building a category of pro object in C, which is a category with all limits and which is universal for that property. So there is a finite limit preserving functor from C to pro C, and pro C is a pseudo-initial for this structure. And a very well-known fact is that if you start from the category of finite sets and you take the pro-completion, then you get the category of pro-finite space, or the stone space, basically. So the opposite of Boolean algebra. And so what I mean by that is that the finite set corresponds to the discrete stone space, and this inclusion of finite set into stone space is the universal pro-completion. But one could, try to generalize that to say that like pro-discrete space are like the pro-object in the category of set, or pro-discrete space from the pro-completion of the category of set. But it's well known that this doesn't work, and we'll see a little bit later exactly why that doesn't work. But one first correction that we can try to make is to replace spaces by locale. So it's still not going to work, but it's going to be a little bit closer to being accurate. So I didn't really know how much the audience would know about locale. So I won't use a lot about locale, just that everything I'm going to do is just false for topological space, and it works with locale. But in practice, I'm not going to use anything from locale theory explicitly in the talk. So I just want to give a very, very quick recall of what a locale is, but you don't need to know much about them. So a locale is it's very similar to a topological space, but instead of defining the topology as a collection of subsets, we define the topology, so this O of X, as an abstract poset. So just a set with an order. And OX is like this the collection of open subspace of X, open subspace. And we assume that we have arbitrary unions, so supremum and finite intersection, infimum, and that need to satisfy the distributivity law, infinite distributivity of intersection over union. And morphism of locale, they are defined as a map going the other way between the posets that preserve arbitrary union and finite intersection, and you think about it as a preimage of an open subset, so open subspace. So typically any topological space, you can think of it as a locale, but just forgetting the set of points and just remembering the abstract order set of open. So we say that the map of locale is surjective if this F-1 is actually injective. And so a topological space from this perspective is exactly the data of a locale X together with a discrete set and a surjective map from S to X, where I see the discrete set as a discrete topological space, and so as a discrete locale. So it's like the locale whose open subspace are all subsets of S. And so, as you probably know, if you start from a general locale, there is like a universal discrete set S with a map to X, which is a set of points. But in general, this might not be surjective. For example, S can be empty without X being non-trivial. Anyway, I'm going to say that a locale is prodiscrete if it can be written as a limit of discrete locale. And so I'm going to denote Z, the category of prodiscrete locale. And it's a category that has all limits. And so we get an essentially unique limit preserving functor from pro set to Z, which sends a set to the corresponding discrete space, discrete locale. But the thing is, there's many objects in the image of that functor that have no point. In fact, most example we have of local without points are prodiscrete. Like for example, every complete Boolean algebra correspond to a prodiscrete local. And so just for completeness, there is also a topological characterization of prodiscrete local, and there's what we call the strongly zero-dimensional local. So meaning there's a local that have a basis of Klopen subspace, and such that each covering can be refined into a covering by disjoint Klopen subspace. So they are basically the things that are of Lebesgue dimension 0. Right. So this functor that we have here from pro set to Z, it's still not an equivalence of category, and I want to explain why very quickly. So for that, I'm going to consider the following example of a pro set. So for each n, I can look at the set an of integer bigger than n, and I can form their intersection. So as a set, obviously, A infinity is empty. There's no integer bigger than n for all n. But if you define A infinity as a limit and you take that limit in the category pro set, then you get a non-trivial object. So how do we see it's non-trivial? Is because if I take any set X, I can compute what are the map from A infinity to X. And so due to how the category pro set is constructed, I will go over that a bit later, we can see that this is just the colimit over n of function from an to x. And so those are just germs of function from n to x. By that, I mean function from n to x up to equality almost everywhere. So equality outside a finite set. And so A infinity is a non-trivial object because we have a lot of maps from A infinity to other sets. But if now you take the image of that in the category of local, and meaning you take this intersection over here in the category of local, then you get the empty space. And also we'll see why a little bit later. And so it shows that there are some non-trivial objects in process that gets sent to empty space in local, and so the functor is very far from being an equivalence, or at least we lose some information when we go to Z. And so this means two things. It means that we don't have, at least not this way, a geometric description of the object of pro set. And also we don't have a nice universal property for the category of prodiscrete local, like we have for pro-finite space. And so in this talk, I'm going to deal with the second point. I'm going to give you a very nice universal property for the category of prodiscrete local, which has to do with extensivity. So one reason why I was interested in that is because in the homotopy theory, if you start from a general topological space, it's known that you can actually put a topology on its homotopy group, which is a prodiscrete topology. And actually, as mentioned in the previous talk, there is also, well, not exactly mentioned in the previous talk, but very related to things that were mentioned in the previous talk. In topos theory, there is a way to attach some homotopy group or homotopy type to a topos. So they were known as the Artin-Mazur homotopy type or pro-homotopy type, and this has been generalized by Lurie into what's called shape theory for infinite topos. But the thing is, the object you get this way naturally are naturally pro objects. So like the homotopy group are in pro set or pro group. The homotopy type are pro homotopy type, and so on. And we kind of want to like connect the two point of view. And what I wanted to understand better is what it means that those pro sets that we get, for example, the pi zero of a topos is a pro set. Why is it a pro-discrete space? And this is what I'm going to explain. And ideally, we would like to develop a higher categorical version of that to study the whole pro-homotopy type and not just the pi zero. But the one categorical version is a good place to start. Okay, so one more preliminary I need to mention. I need to recall what an extensive category is. So it's one of the condition in Giro characterization of toposes. So a category is extensive if if it has finite limit and coproduct first. So there is a notion of extensive category without finite limits. I won't go into that. For me, I'm gonna always assume my category have finite limits. And so in this case, extensivity just means that this functor I've represented here is an equivalence of category, meaning that an object over a coproduct can always be decomposed in an essentially unique way into a coproduct with an object over each component. So an object over X coproduct Y is a coproduct of A and B with A over X and B over Y. So this is a finitely extensive category. And what I'm going to call an extensive category is the infinitary version, where we have more generally an equivalence of category between C over a coproduct and collection of objects of the slice C over Xi. So this is what usually called like a completely extensive or infinitely extensive, infinitary extensive category. I will just say extensive because this is the only type of extensivity I'm going to consider. And by this equivalence of category, I mean given by the same kind of functors than in the previous definition. Okay, so first thing is that the category pro set, it's finitely extensive, but it's not an extensive category. It's not fully extensive. And we can actually see that from the exact same example as before, this A infinity, so which, so A infinity is the intersection of all the AK and or AN, and AN is a set of integer bigger than N. And so it's a subset of N, so it comes with a map to N, and N is a coproduct. It's a coproduct of one index by N. But if I look at all the fiber over each element of N, this is going to be empty because A infinity is defined as that intersection, and limits commute together, so you can compute the fiber very easily, and you see that it's an intersection of like a finite number of singleton and then infinite number of empty set after that, so it's empty. So all the fiber are empty, and so it's impossible to write A infinity as such a coproduct because there is not a single object, non-empty object that has a map to A infinity that factor into one of the components of N. So this shows that extensivity fails. And this is actually exactly how we prove that this limit defining A infinity is empty in the category of locale. It's because the category of locale is extensive. And so we can do the same computation in locale to show that A infinity is empty there. Okay, and so that kind of suggests that extensivity play a big role in the difference between Z and proset, because the way we actually prove they are different is by showing that one is extensive and the other is not. And this is basically the main point of the talk, is that the category Z of prodiscrete locale is actually the initial extensive and complete category. So this is kind of the main result, not the only one, but the main result of the talk. So prodiscrete locale are a pro-completion of the category of set, but in a way that preserve extensivity. If you just take the pro-completion, you don't get an extensive category. But if you try to take the pro-completion in a way so that the result is an extensive category, then you get the category of prodiscrete locale. And because category of geometric objects tend to be extensive, so for example, as I said, the category of locale is extensive, the category of topological space is extensive, or every topos is extensive, the category of scheme is extensive. It's kind of suggests that prodiscrete locale are like that. It's probably not gonna be easy to find a geometric description for prosets beyond this case of prodiscrete locale. So yeah, what I mean exactly by that theorem is that if for any category C, which is both complete and extensive, there is a essentially unique functor from Z to C that preserves both coproduct and limits. And yeah, so that's that. And a further thing we get during the proof is that for any extensive complete category C, this essentially unique functor from Z to C actually is always a right adjoint functor. It preserves limits, but in part it's even more than that. It's a right adjoint, and the left adjoint is something we can think about as a pi zero. It takes an object of C and gives you a prodiscrete space, prodiscrete locale. And there is a more concrete way in which we can think of pi zero as a fundamental, well, as the pi0, is that if I take any set S, then in my extensive category, I can build this object that I'm going to denote S underline, which is just the coproduct for S in S of 1. And so this is like a discrete object in C. Like if you for example, in topological space or local, it gives you the discrete topological space or local. The adjunction formula for pi0 exactly say that function from a general object X in C to those discrete objects are the same as continuous map from the pi0 to set. So yeah, it's the sort of universal property you expect from a pi0. Okay, so those are the main theorem, and in the rest of the talk, I want to explain a little bit some ideas that goes into the proof. I won't do the proof in detail. This is not the place, but there are some very interesting things going on here, so I want to talk a little bit about them. So let me very briefly recall how the pro-completion is constructed in general. So for a small category with finite limit, you can always define the pro-completion as follow. You take the category of finite limit preserving functor, which I'm going to denote by lex for left exact. So you take the category of finite limit preserving functor from C to set, and you take the opposite category of that. And this is the pro-completion. And the functor from C to the pro-completion is just the Yoneda embedding. And if you get a finite limit preserving functor from C to something else, which is complete, then the way you get the universal functor is you first build a kind of like nerve functor, which goes from D to that category of finite limit preserving functor, which send every object of D to the arm of D into F of object of C. And this functor, it always have a right adjoint from this category of this lex up to D, and this is the essentially unique functor that's claimed by the universal property of the pro-completion. So we have this very concrete description when C is small. So unfortunately, set is not small, and there is a version of that for non-small category, which in the case of set simplify as follow. So proset is the full subcategory of endofunctor of the category of set, which are accessible and preserve finite limits with an op. And when you do the same construction that I explained before to build the universal functor, so you still get out of any functor from set to D, which preserve finite limits, you still get a functor from D to endofunctor by taking this kind of like nerve where you arm into F of any set. But this time, this functor does not always have a right adjoint, but it has a partial right adjoint, which is defined on accessible functors. Right. So this category proset, it has all small limits and co-limits. And co-limits are just computed as limit of endofunctors. So limit in sets, basically, level-wise limits. So the terminal, so limits in proset are sometimes a bit complicated to describe, but the terminal object is fairly easy. So the terminal object of proset is the representable functor corresponding to the terminal object of set. And this is just because the inclusion of set into proset preserves finite limits, so it preserves the terminal object in particular. And so this representable is just the identity functor. So the terminal object of proset corresponds to the identity functor. Or if you prefer, the identity functor is initial in the category of endofunctor preserving finite limits. And so in proset, when we build those like discrete objects, those coproducts of the terminal object, well, we can compute easily what they are because colimits are computed as coproduct are computed as products of endofunctor, and the terminal object is the identity. And so we get that the discrete objects are just the representable because S underline of X is just a product for all S of X. And so this is the same as a function from S to X. So the discrete objects are the representable. Now it's the canonical inclusion from set into proset. Okay, so I need one technical tool. I need to introduce a special case of infinite limits, which are going to be interesting later. So if I have any set X over another set S, then I can always write X as a certain wide pullback over S. And by a wide pullback, I mean an infinite product in the size category. And the way I do that, so this is the formula. So this object, S lower star, S upper star X, which is here. So what I mean by S is I'm looking at the map from the singleton to S, corresponding to an element S of S. But concretely, this S lower star, S upper star X is the object over S whose fiber over small s is the same as the fiber of X, but all the other fiber are 1. So you take a point in S, you have X, which is over S, and you collapse all the fiber except the one you've chosen to a singleton, and you keep one fiber to be the same as the fiber of X. And so if I do the wide pullback of all those objects indexed by S, so it's wide pullback over S and indexed by S, you recover X. Because if you look at the fiber over any elements of S, you get a product of an infinite family, but with all of them except one are singleton. Right, so this is a kind of very tautological limit, but it's actually an infinite pullback. And so this specific limit, I'm gonna call it the fiber decomposition of X over S. And I'm gonna be interested in functors that preserve those fiber decomposition, because even if it's a very tautological limit in the category of set, a functors that just preserve finite limits has no reason to preserve that specific limit. And so this notion of functors that preserve fiber decomposition is closely related to extensivity in the following ways. So if I take a proset F, then the following conditions are equivalent. So I see F as an endofunctor of the category of set. And one of the conditions is that F preserves those fiber decomposition of all map X to S for some fixed S. And the other one is that anytime you have a map in proset from F to the discrete object at S, then you can decompose F as an S index coproduct as if the category was extensive. So basically, to get this category of proset to be extensive, to behave as an extensive category, you need to assume that you're considering objects that preserve fiber decomposition. So yeah, we have this connection between extensivity and fiber decomposition, and there is another one, which is that if you have an extensive category C, then the unique coproduct preserving functor that takes a set to the discrete S, so the same thing as before, the coproduct over S of 1, then this functor, it always preserves both finite limit and fiber decomposition. So this is when C is an extensive category. Right, so this is how those fiber decomposition and extensivity are related. And this notion of fiber decomposition, it also very crucially connect to the notion of prodiscrete local. So this is the following theorem, which is one of the key, this is basically the central result of the paper. So given a functor from set to set, the following conditions are equivalent. The first one is that F preserves all finite limit and fiber decomposition. So finite limit and those specific infinite wide pullback. And the second one is that F can be represented by a local, meaning that there is a local L such that F of S is our continuous function from L to the set S. And the third condition is that if you assume the local to be, you can assume the local to be prodiscrete, and if you do so, it's unique. So you have a unique prodiscrete local L, such that F of S are a function from L to S. And, And those conditions actually imply that the functor F is accessible. So it's kind of surprising of the first condition that from just assuming preservation of finite limits and fiber decomposition, you get accessibility. So preservation of like filtered colimit of some rank. But it's much more obvious on condition 2 and 3 because it's easy to see that functors represented by a local are accessible because like any function from a local to a set S is going to factor in some set of cardinality smaller than like the power set of the associate frame or something like that. So that gives us automatically accessibility. So I won't do the proof of that theorem, but this is really the central result of the paper. So I want to give an idea of how the proof work. And so the interesting part is basically the proof that 1 implies 3. 2 implies 1 is actually one of the two lemma of the previous page. It's a consequence of one of the two lemma from the previous slide. And 3 implies 2 is tautological. So and the way you build this prodiscrete local L that represent F is as follows. You start by looking at the Boolean algebra f of 2. So by 2, I mean the two element sets, which is a Boolean algebra. And because f preserves finite limit, it preserves in particular product. So it's send Boolean algebra to Boolean algebra. So f of 2 is a Boolean algebra. And we can undo it with a certain Grothendieck topology. It's a poset, and we can put a Grothendieck topology on it, where for every element of f of s, I can build a certain family of element of f of 2 by taking all the image of that element by characteristic function of singletons. And so this gives a family of element of f of 2. It's actually a disjoint family in the Boolean algebra. And I'm going to say that this family is a covering of the top element. And so this defines generates a Grothendieck topology. And we take the associated sheaf topos, which is actually a local. And we then, by applying many times the fiber decomposition, the preservation of fiber decomposition, we gradually show that this local we just constructed actually represents the functor f. Okay, and so we can refine this a little bit, and actually the category of prodiscrete local is equivalent to the opposite of the category of endofunctor of set, which preserve finite limit and fiber decomposition by that construction. And all those functors are automatically accessible. Okay, and so this is really the core of the construction, that and the connection between preservation of fiber decomposition and extensivity. And so we can put everything together and actually prove the main theorem. So let me just recall what we need to do. So my claim is that for any extensive and complete category C, there is an essentially unique functor from Z to C, which preserve coproducts and limits. And moreover, this functor has a left adjoint, which is this pi0 functor. And so if I take a complete and extensive category C, so I still have my unique coproduct preserving functor from sets, sending every set to the discrete object, so coproduct of 1. And as I said before, because C is extensive, this functor preserves finite limit and fiber decomposition. And so the induced functor I get, the one that will appear if I wanted to extend this into a functor from proset into C. So this is the functor from C to the endofunctor of set that send every object of CD to the endofunctor that set the set to from D to the discrete corresponding discrete object. And so because that functor here underline preserve finite limit and fiber decomposition, this functor here actually factors into the category Z. So the whole functor from C to Lex set setup actually factor through the inclusion of the category Z. And as we have seen, the functor corresponding to prodiscrete local are automatically accessible, so we're already inside the category proset. And so we get our pi0 functor here from C to Z. And because we have a partial left adjoint from proset to C, we actually get a factorization of adjoint functor. And so we get the adjunction between C and Z over here. And so at the end of the day, the universal functor is this arrow to the left here from Z to C. Okay, so this is basically the proof of the theorem. And let me just very quickly end by giving you a kind of an explicit description of what this pi zero of x is. So if I have C, a complete extensive category, and X an object of C, then pi zero is constructed as follow. So the Boolean algebra of Klopen subspace of this pi zero of X is the Boolean algebra of complemented subobject of X. In an extensive category, you get a Boolean algebra of complemented subobjects. And this complemented subset form a basis for the topology of P0 of X, which is a local. I mean, I'm saying topology, but it's a local, not a topological space. And pi zero of X is obtained by putting a Boolean Grothendieck topology on this Boolean algebra, in which a family is a covering if and only if it can be refined into a family of subobjects such that X is the disjoint coproduct of the subject. So even more explicitly, an open subset, open subspace, I should say, of pi zero of X is a collection U of complemented subobject, like a C, a sieve of complemented subobjects. By that, I mean that if you have an inclusion of complemented subobject and the big one is in U and the small one is also in U, which is closed under a disjoint union. So if you have a disjoint family of complemented subset which are all in U, then their coproduct, which is also complemented subobject of X, is in U. If the coproduct is a complemented subobject of X, then it's in U. And that's everything I wanted to say. So thank you very much for your attention. And if you have any question.
Okay, so thank you, Simon, for your nice talk. And now we have some time for questions. I also have questions, but I will be the last one, I promise. So if there are questions from the audience, please people can unmute themselves and ask the question. So I see Christoph raise his hand. Christoph, please go.
Yeah, so thank you for the talk, and I have a question. So like, if you have a functor from set to set, then of course it will preserve automatically those effective epis whose codomain is a point, because it's obvious. And if you have this preservation of fiber decompositions, then does that imply that your functor is regular? So like it preserves surjections?
That's a good question. I need to think for 1 second. So we know it's representable by a local. So if I have a map from a local and a surjection, of course. Wait. If you have a surjection instead, then it's a split epi, so it's preserved by any functor.
Oh, sure. Yes. Okay, so I just wanted to say that in the lecture notes of Lurie, there is a theorem which says that if you have some coherent category with disjoint coproducts or something like that, then if you have some regular functor, then you can always replace it, some regular functor from that category to set, then you can always replace it with a coherent functor from that category to sheaves on F2. So like in this case, you also constructed this Boolean algebra F2. And so for this functor that you started with, you can see it then as a functor, as a coherent functor from set to sheaves on F2. And I don't know.
Yeah, I need to look at it, but from what I think I've seen that construction before, and I need to look at it in more closely, but I feel like it would correspond to like a profinite version instead of prodiscrete, because everything is coherent, and so you only have finite scope product. But I would have to look at it more closely because I don't exactly remember what Lurie does in his notes.
Okay.
So I'm not sure I can say more at this point.
Do we have other questions? Okay, so if not, I have two comments.
Mhm.
So the first one is concerning slide 11,
Okay,
which is,
1 second.
yes, the characterization about functors into locales. Oh,
Previous one, maybe? No. No, the next one. No, still not.
okay, maybe I'm crazy, but you understand what I'm talking about.
Yeah,
So here there is a paper
yeah,
by,
this one.
exactly, thank you. There is a paper by Blas. The title is Exact Functors and Measurable Cardinals, where he talks about exact functors of set.
Mhm.
It gives a characterizations via ultra filters, and he calls them like reduced powers. This is how he calls them. And I was wondering,
Interesting.
is there any connection between this and what you're doing there? Because it feels
I
there could
I
be.
have no idea because I haven't looked. I'm not sure I've looked at that recently or ever. So I would have to look at it. It's definitely possible.
And then a similar question. In the last 3 years, there are some papers by Karatzeris, and he studies exact and regular categories of locales. Is there any connection of this work with yours that you are aware of?
I don't think so.
Okay.
But yeah, again, I would have to really look at it more closely. To be honest, I was mostly concerned with how this would generalize to the higher categorical setting, so I haven't looked at the local literature that much. But yeah, I should look at it.
Okay. Thank you. I will send you an email with the references.
Yeah, thank you very much.
Thank you. And oh, I am the chair, sorry. Is there any other question from the audience?
Maybe a very vague one.
Yeah. Yes.
So I mean, this procedure like of extracting this prodiscrete locality reminded me of the fact that you can assemble shape as a say a global thing. So it's a functor from all topoi to pro spaces, say, or pro
Yeah.
sets.
Yeah, absolutely.
And
yeah, this would be the generalization of the pi0 construction.
Yeah. Yeah. And I guess this as a right adjoint. And the way to describe this right adjoint is I take spaces and I go to topoi. This is fully faithful because I take like each space to the slice, say, or
yeah, absolutely.
And then I can extend it by limits. And this gives me a functor, and this is right adjoint to the shape.
Yeah.
And I don't know, in some sense, I mean, this topos that you get, it looks a bit like the prodiscrete locale that you were talking about.
Absolutely. This is exactly what I have in mind. So if you replace sets by space, if you define extensivity in terms of groupoid index coproduct, infinity groupoid index coproduct, then what I've talked about today, the hope is that it carries over to infinity category and it gives the shape as a prodiscrete topos. So a limit of those topos coming from sets. Yeah, by discrete, I mean one that's coming from just a space here.
Infinity groupoid, yeah.
Yeah, which is a slice of the category infinity groupoid.
I see. And so the point is that you want to have this construction, but not starting from topoi, but something slightly more.
So, for example, it's maybe I'm wrong about this, but it's not clear to me that. So one of the things I'm showing here is that. So I have this adjunction between so local and proset, so which would be an adjunction between infinity topos and prospace.
Mm-hmm.
And for local, I know how to prove that this adjunction is idempotent. It's not so clear to me that this is known for infinity topos, that we have that the adjunction is idempotent. Maybe it is.
So you mean that the shape of this thing that you get should be the same as the.
Yeah, exactly. And that if you
so it's not. This is not true. I think
this is not true.
It's not true that pro spaces is fully faithfully embedded.
Yeah.
If you restrict to
so no, prospace is not fully faithful. That's clear. But that a certain localization of prospace is going to be fully faithful. This is what what idempotent adjunction would mean.
Okay. Okay. Sorry, I misinterpreted. This I don't know. This I don't know.
Yeah, exactly. And I think this is a not known, and this is a sort of thing I would like to understand, because that's what I'm showing in the one categorical case, that there is a localization of proset which correspond to prodiscrete local, and those are exactly the thing you get out of a pi0 of a topos or of a local.
I understand. Thanks.
Thanks.
Okay, so thank you. We have our last round of silent applause for Simon. Thank you, Simon, for your talk. And there is no further time for questions, unfortunately.